Hello everyone, welcome to Happy Chemistry. Let's begin today's episode. Uncertainty in measurements. In this episode, we will talk about the qualitative aspects of the uncertainty as shown in the outline. Let's first talk about exact and inexact numbers. In scientific work, there are two types of numbers, exact numbers and inexact numbers. Exact numbers are numbers that are fixed. The conversion factors and the constants such as speed of light, gas constant, Planck constant belong to this category. All scientific measurements are inexact numbers. Why do we say all measurements are inexact numbers? All measurements have an associated uncertainty. This uncertainty is caused by different errors. Different errors that occur during the measuring process. Therefore, due to these errors, there is an uncertainty associated with measurements which make them inexact numbers. To understand the uncertainty associated with measurements, it is important to understand the types of errors that can occur. There are two types of errors: systematic errors and random errors. These are also called the determinate and indeterminate errors. We will look at the nature of these errors, reason for occurrence, origin of the reason, and what to do to eliminate or minimize the errors. First, we will compare the nature of the systematic and random errors. Systematic error is consistently occurring and hence reproducible. It can be detected, corrected, and eliminated. Random error is not consistently occurring and hence not reproducible. It cannot be detected. Therefore, random error cannot be corrected or eliminated. However, certain ways can minimize random error. Both systematic and random error can be negative or positive deviations. Let's now see the reason and the origin of reason for systematic and random errors. Systematic errors occur due to instrumental errors such as incorrect calibration and tolerance limits, or flaw in the experimental design. Random errors occur due to personal errors such as individual differences in taking measurements or electrical noise. Most importantly, how to eliminate or minimize these errors. Systematic error can be eliminated by detecting and correcting the instrumental error and having corrected experimental design. As I mentioned, random error cannot be eliminated. However, it can be minimized. The way to minimize random error is practice the correct techniques for obtaining measurements and taking repeated measurements. As I mentioned earlier, systematic error can be detected. Now we will discuss the ways the systematic error can be detected. There are 4 methods. First, analyze a known sample such as a certified reference material. The method should produce the known answer. If it is not producing the expected known answer, then there is a systematic error. Second, analyze the blank samples. That means samples without the interested analyte. The method should produce a zero result. If the method is producing a non-zero result, then there is a systematic error. Third, using different analytical methods to analyze identical samples. The methods should produce the same result. If there is a discrepancy, there is a systematic error. Finally, carrying out round-robin experiments. That means different personnel from different laboratories using same or different methods to analyze identical samples. The results should be within the estimated random error. If the discrepancy is beyond the estimated random error, then there is a systematic error. These are the 4 methods to detect the systematic error. Once detected, immediately should be corrected and be eliminated. When considering uncertainty, accuracy and precision are 2 important concepts. Accuracy. Accuracy is a measure that indicates how closely the individual measurements agree with the true value. That means nearness to the truth. Precision. Precision is a measure that indicates how closely the individual measurements agree with one another. That means reproducibility. The most common way to illustrate the concept is the dots in a dashboard, where center is the target. Dashboard A has all the dots or all the measurements near the target. That means they are close to the true value. And the values are close to each other. That means the dashboard is an example for good accuracy and good precision. Dashboard B has all the dots away from the target. They are not close to the true value. However, all of them are close to each other. That means the dashboard is an example for poor accuracy and good precision. Dashboard C has all the dots around the target. Therefore, they can be considered as close enough to the true value. However, they are not close enough to each other. That means the dashboard is an example for good accuracy and poor precision. Dashboard D has all the dots all over the place. They are randomly spread. That means they are not close to the true value or not close enough to each other. This dashboard is an example of poor accuracy and poor precision. As scientists, when we take measurements, the measurements should look like dashboard A. Measurements with good accuracy and good precision. If we get either poor accuracy or poor precision, we have to eliminate systematic errors and minimize random errors. Now we will see how to report uncertainty. When expressing scientific measurements, it is important to indicate the uncertainty associated with it. By keeping the significant figures accurately allows us to indicate the uncertainty properly using the plus or minus notion. General rule is In scientific measurements, there is always some uncertainty associated with the last digit. The number that includes the last digit with uncertainty is called the tolerance limit. All the digits including the uncertain one is significant. We will see an example. You want to measure some sugar. Let's say you want to measure about 50 grams. You have two balances. One with tolerance limit 0.01 gram and one with tolerance limit 0.0001 gram. That means balance number 1 can measure up to nearest 0.01 gram and balance number 2 can measure up to nearest 0.0001 gram. So how can we express the measurement with uncertainty? Is that for balance number 1, 50 plus or minus 0.01 gram, and for balance number 2, 50 plus or minus 0.0001 gram. If you see in terms of significant figures, the representation is not accurate. The accurate representation for balance number 1 is 50.23 plus or minus 0.01 gram. And for balance number 2, the accurate representation is 50.2358 plus or minus 0.0001 gram. In balance number 1, the measured weight can be between 50.22 to 50.24 grams. In balance number 2, the measured weight can be between 50.2357 to 50.2359 grams. You can see how the uncertainty is associated with last digit. And better the tolerance limit, lesser the uncertainty. That means with tolerance limit 0.0001 gram, there is lesser uncertainty compared with tolerance limit 0.01 grams. So here's the way to indicate the uncertainty associated with scientific measurements. In summary, we talked about exact and inexact numbers, uncertainty in measurements, types of error, that means systematic and random error, detecting systematic error, accuracy and precision, illustration of accuracy and precision concepts, and indication of uncertainty using significant figures. That's the end of today's episode. Hope you liked the video. Give it a big thumbs up. Leave your comments and questions below. Subscribe to my channel and turn on the notifications to be notified as soon as a new video is uploaded. Don't forget to follow me on Facebook and Instagram. Thank you very much for watching. Stay tuned. See you in my next video. Until then, happy chemistry. Bye bye.